So I'm Lukasz from Heliax. I will be talking about compiling the functional programming language Juvix to the Cairo zero-knowledge virtual machine. But actually, most of the presentation will not be very Cairo-specific. So what I will be trying to describe is mostly the Juvix compilation pipeline in general, and how you ultimately get Cairo assembly out of it. And what I hope to convey here is like the general architecture of this pipeline, and hopefully convince you a bit that this architecture lends itself well to adding new backends. So in principle, a lot of what I will be talking about could be reused when you wanted to target a different zero-knowledge virtual machine than Cairo specifically. Okay. So first, what is Juvix? Juvix is a purely functional programming language we've been developing at Heliax for around 3 years now, intended for to be used for intent-centric, privacy-preserving applications on Anoma. Okay. So it is a strongly statically typed language with eager evaluation. It is broadly in the ML family. Like by ML family, I mean it like kind of very broadly. This is like a family of strongly statically typed functional languages. So, for instance, like it is a bit similar to OCaml and Haskell. Like if you add dependent types, then like Lean or Agda could broadly be put.
Sorry. How is Haskell eagerly evaluated?
No. I don't mean Haskell is eagerly evaluated. I mean that this language is broadly in the broad ML family, which contains languages such as these. Not all of them are eagerly evaluated. All of them are statically typed. Yes, so that's what I meant. Sorry for the confusion. But Juvix specifically is eagerly evaluated. Haskell is not. Okay, and the idea with the Juvix compiler is that it should be easy to integrate different compilation targets. Okay, so why do we need Juvix? So the idea is to use Juvix for the business logic in Anoma. Juvix is declarative and functional, which kind of matches the Anoma architecture where we have declarative resource logics, and Juvix is mostly used for those, also for transaction functions that create transactions. Juvix has static typing, which gives us some formal guarantees about our programs. It also has, for instance, termination checking. In the future, we probably want to add more static analysis. It is relatively simple, maybe clarifying a bit. It has lots of features, but what is relatively simple here is like the core language that those features later desugar to, which is a simple language based on lambda calculus, and then it lends itself well to, because of its relative simplicity, it lends itself well to compiling it to different targets. Okay, so it has multiple backends already. So we can compile to the transparent Anoma virtual machine. We can compile to native code and also WebAssembly, currently via C. We can compile to Cairo. There is also a RISC-0 backend, which is in a very initial stage, but it's already there. Formerly, we had compilation to ZK-LLVM, for instance, though we discontinued it because it wasn't the ZK-LLVM project wasn't mature enough at that time. We also had compilation to arithmetic circuits through Vampire, but we no longer support that. And it is comparatively easy to add new backends. Of course, it does require some work, but I would say if you try to like add a new target to say, let's say Haskell or Rust, that is much more difficult and requires more work than adding it to the Juvix compiler. Okay, so here is an example Juvix program. Which demonstrates like several features of the language. So first of all, we have algebraic data types. Here we have the type list that has a type parameter a and has two constructors, nil, and let's pronounce this double colon as cons. So nil has no arguments, cons has a head, which is of type A, and a tail, which is of type list A. Then this open list thing makes those constructors available in the global namespace. We declare like some syntax to make this double colon infix, and then we have a map function that is polymorphic in A and B. In those curly braces, we put the types. It takes a function f from A to B and a list of A's and returns a list of B's. And here we have the syntax for pattern matching. For if this list argument is nil, then it returns nil. If it has a head x and a tail xs, then it uses the function f on x and recursively maps f on x's and well, consis the result of that. All right. So now Cairo. Cairo is like a Turing-complete, Stark-friendly CPU architecture for generating zero-knowledge proofs of program execution integrity. So it is a zero-knowledge virtual machine. The sort of language of this virtual machine is a low-level imperative assembly. Roughly, it has it is a reduced instruction set architecture. The sort of non-standard things about it is that memory in Cairo is in fact read-only and non-deterministic. This means that, strictly speaking, we do not have assignments in Cairo. What we really do is we assert equalities between different locations in memory, and well, the sort of execution of the Cairo virtual machine is successful if roughly the Cairo virtual machine can figure out that those assertions are consistent. Another thing that is specific to the implementation of the Cairo zero-knowledge virtual machine and generates some difficulties when trying to compile, when trying to target it, is that memory accesses are required to be continuous, meaning that if you assert some equality about some memory address, this needs to be continuous with no gaps. So you can't say something like this, that something at address 0 is equal to something, then don't do anything, and say later on something at address 100 is equal to something, because then you have a gap between the 0 and 100 in terms of memory accesses. You haven't said anything about what's in between. You can't do it. You need to say what's at address 0, then you need to say what's at address 1, then what's at address 2, and so on. That's a requirement that the Cairo virtual machine in practice enforces. Okay, so here is some example program in Cairo assembly. Don't look too much into that. It's just to give you a feel of how it looks like. It's like very low level. This AP is a register. In those square brackets, we are accessing memory at address determined by the register AP. Here is like it computes the factorial of 10. So well, we count down and multiplying the numbers. Here we have some jumps. We can increase the number of we can like modify the AP register. We have some conditional jump. As I said, don't don't try to understand too much out of it. Like at the end, we get the result in at this memory location. Well, the point here is to give you like some rough idea of what we're dealing with. So we have this high-level language that we somehow need to compile down to something like this. All right. So here is the overview of the Juvix compilation pipeline. So the idea with the pipeline is that we divide it into many different intermediate representations, and the idea is to compile down the features of Juvix one by one, step by step, using those different intermediate representations. The most important, perhaps, is the Juvix core here, which is the minimal lambda calculus-based functional language that I've been mentioning before. So after type checking and desugaring, we have some representation of a Juvix program in Juvix core. We do some transformations on it, and then we have other intermediate representations. Ultimately, we generate Cairo bytecode, and the point is that those intermediate representations can be reused to target different backends, depending on what kind of thing we are targeting. For instance, we have this Juvix ASM, which is a stack machine. So if we wanted to compile to something that is a stack machine, for instance, directly generate WebAssembly instructions, then we could plug it in there. That's the idea of sort of breaking this up into those little steps, that when you then want to add a new backend, you can find a place in your pipeline where you want to put it. All right. And I will now very briefly talk about those different intermediate representations. I have quite a few things on the slides. Perhaps I will skip a bit of them. So first, the Juvix core. Juvix core is a minimalistic functional intermediate representation based on the lambda calculus. That's what Juvix programs desugar to after type checking. Well, briefly how it looks like. So you have application, you can apply to things. You have lambdas, that is anonymous functions. You have some lets. You have matches, that here the patterns can be nested patterns. And you have also cases, which are one-level case expressions, which have exactly this form. Here you can't have nested patterns. You just have constructor and the variables for the arguments of the constructor, just single level. And as you might guess, one of the transformations on this intermediate representation is to compile those matches with complex patterns to case expressions. So an example Juvix core program. So for this map function, well, after type checking and sort of desugaring syntax, you end up with an initial Juvix core representation that looks like this. Here it's like kind of everything is explicit. So you know those here the type parameter for the inductive type of lists is here explicit. Here those type arguments are explicit, and so on. So initially you after desugaring Juvix to Juvix core, you end up with something like this. All right, let's go further. So what do you do then? As I mentioned, you need to compile those complex patterns. Here, there is only one level, so it's not difficult, but in principle, you can have nested patterns here. So like you could have cons of X, of cons of something, and so on, and you need to break it up into single level cases. All right. We also then need to do lambda lifting to remove anonymous and local functions. And ultimately, we erase the runtime type information, that is all those extra type arguments that we have, so that they don't crop up in our programs. And we do also a bunch of other things. These are like the three, let's say, most important things that to understand roughly what's going on. We also do some optimization and like a bunch of other things. But now let's look at what happens with this program in Juvix core when we've done those things. So as you see, we have compiled the match to a case. Lambda lifting didn't do anything because we didn't have any anonymous functions here. We removed this type information in constructors, so now there are no type arguments anywhere, and we've converted the polymorphic types in the type signatures into this star, which signifies a universal type, like so anything has this type star. All right. Yes.
Just one very basic question. Is list, what is list if you said you erase type information?
I didn't show this on the slide, so now list is still an inductive type, but you did the same kind of erasing in the definition of list. So now you have a cons which has a which is star list.
Thank you.
Okay, and what we get after doing all those transformations on core is we get what we call a stripped Juvix core representation, and it has the following properties. That all functions are defined at the top level, meaning that there are no nested or anonymous functions. We got rid of them by lambda lifting, so we have just a bunch of functions, bunch of functions definitions, and functions are simply typed, including this universal type, with the number of arguments matching the type, meaning that, well, if someone knows what eta expansion is, then they are fully eta expanded, meaning that, here we have, for instance, two arguments, the function and the list, and this is indicated in the type. So the top lambda abstractions here will correspond to the type always. So there will be as many lambda abstractions as you have arguments indicated by the type. All right, and another thing is that we've transformed it in such a way that all application expressions have this form, with f being one of a function name, a variable, or a constructor. So it now, after these transformations, also some transformations I didn't show, it cannot be anything else. And then once we have this, we can transform, and also polymorphic arguments have this universal type. We can transform this thing further to another representation, which is Juvix tree, an applicative functional intermediate representation with explicit closure operators and uncarried top-level functions. So in the interest of time, maybe I will go very quickly through this. So just to give you a brief idea what's going on here, what kinds of expressions we can have. So we can reference the nth function argument. We no longer have names for them, or at least not necessarily. They are referenced by by the argument number. We have some stack for the temporary variables, temporary values. We can push onto the stack. So here we push the value of evaluating t inside exp and pop afterwards. We can reference the values in the temporary stack. We can branch on booleans. we can allocate constructor data. Constructor data consists of a tag, which indicates which constructor we are talking about, and the representations of the constructor arguments and the data for the arguments. And here we have some expression that does this allocation, indicates the constructor tag and the arguments. We can then branch on the constructor tag, and we can reference the kth argument of constructor data. All right, and very briefly, the whole. And okay, so we then have different ways to call a function, because now we begin to at this point we begin to distinguish between functions that we know and functions that have been allocated, because, for instance, like in this map, we had like some function argument which comes from outside, so we actually need to allocate some data for that function because we don't know which function we are calling, and that data is called closure, which is function called plus environment. This environment is just the arguments that have been applied to the function already. And because we don't have that much time, I will skip a bit here and just tell you the general point of this. So the general point of this translation from Juvix core to Juvix 3 is to choose the right operation for every occurrence of an application, because now we need to kind of distinguish what we should do exactly. So depending on how many arguments are provided, how many arguments a function expects, and what kind of function we'll call in, we either need to choose to call a function directly if we know which function it is, or allocate a closure, or call a closure, or maybe extend the closure, and so on. Or if the thing at the head is a constructor, we need to allocate a constructor. This is not explicit in the Juvix core representation, it is made explicit here. So that's what this translation comprises of, that I've just said. Application translation selects the right Juvix tree operation for each Juvix core application. All right, and well, so that's a part of it. So here is our map compiled to Juvix tree. So as we see here, we had this, for instance, let's look at the cons branch of the case. So we had just in Juvix core we had some applications, but now we choose the right operation for each of those applications. So for cons, this is a constructor, so we will be allocating a constructor. In the let's look first at the second argument. In the second argument, we are calling a known function, map, so we can just do a direct call with the right arguments. Here, this is the most interesting case, but I won't be going into very much detail about that, where f is a variable, so we don't actually know what kind of function that is. And then we have some function that is actually implemented in Juvix tree that does this call to an unknown function, and it kind of figures out what should be done depending on what we actually receive, whether this depending on how many arguments f expects, whether we should call this closure directly, whether we should extend it or call it and then get another closure and call that closure that we get again. So this okay, so this is a version of this function for two arguments, and this is a general function that implements applying an arbitrary closure to two arguments. All right, let's and then we have I will go very briefly over this. Then after that we have Juvix ASM, which is a stack-based imperative assembly language, and the translation basically just linearizes this Juvix tree representation into a sequence of stack-based instructions. And it looks roughly like this. I won't be going too much over that. The point is we just linearized those expressions that we had into something that manipulates a value stack. All right, and then we have another representation that is like a more imperative, let's say, register machine representation of Juvix assembly that uses local variables instead of the stack. What happens there? We just assign variables to each place in the stack and generate this representation. All right, and well, to actually then be able to compile into Cairo, this is more Cairo specific. Now we need to do these two transformations that I will not be going into any detail of what they are, but they are necessary to deal with the peculiarities of Cairo that I mentioned earlier. So we basically need to ensure that each local variable is used only once because of this read-only thing, and we need to do a bit more sophisticated stuff to deal with this continuity requirement. But that's all I will say about that. Okay, so you have this Cairo assembly at the end, which is a textual representation of Cairo bytecode, and here really don't try to understand what's going on, except that, you know, this map got compiled into some relative jump that selects the case and then something happens, but this is just to give you an idea. Okay, so summary. Yes, I mean, I'm trying not to like overrun the time, but yeah, but I mean, here, as I said, I didn't even intend to like talk in detail about like this particular slide because it would require much more time to like explain in detail what's going on with the actual output, just to give you an idea of how this looks. So like the summary of sort of the way I would like to sort of summarize and position it is that Juvix can be seen as a sort of universal zero-knowledge virtual machine front-end language, because as you've seen, most of the pipeline that I've been talking about is not specific to Cairo. Just at the very end, you need to do something to deal with the peculiarities of this particular zero-knowledge virtual machine, but you could reuse almost all of the stuff that has been implemented for this compilation pipeline to target another zero-knowledge virtual machine. Of course, it requires some work, but because of the way the whole thing is structured, it's not that much work. It's doable, and it's perhaps more doable than trying to say target a new zero-knowledge virtual machine from Haskell or Rust. Okay, and well, if you are interested, there is an art report about this whole pipeline, which is very detailed and technical, and it explains in detail what's going on at each step, and you can access it here. And the good thing is that if you like tinkering, you can actually play with yourself with each of the intermediate representations I've shown you. They are like kind of real representations in the sense they have a specific syntax. There is a parser for them. You can run them. You can perform that you can run them with the Juvix command. You can parse them, run them, compile them to compile one to the other, and generally see what happens. Okay, I think that's all I wanted to convey.
Thank you, Lukasz. We have time for one question from the audience, live or virtual, but relatively quick. Jamie.
So the one thing that jumped out to me about the slide that I asked you to go back to is that it looked pretty good. It seemed to be a fairly compact, so I was concerned that the compilation might produce long and inefficient Cairo assembly, but that looks pretty compact.
Yeah,
is that typical?
This is actually what got generated. I just, like modulo editing some comments That's like literally what was generated.
Is that typical? Is this
Yeah, I would say this is typical.
That's really nice. I just wanted to say that looks good.
This is typical, and the reason we can generate relatively good code is that, you know, we do this distinguishing between like different kinds of calls. So you don't do something really stupid with function calls, and this is like very important in a functional language, because function calls are sort of your main way of transferring control. So basically, you implement a loop in essence by doing function calls, and here the compiler can sort of distinguish between a function call that will be compiled just to a jump and a function call that needs something more sophisticated, where you actually have some unknown function. That's one thing. And well, also the pipeline has some optimizations. Like I would say, like some inlining it at the level of Juvix rec. It has copy and constant propagation, so it kind of removes unused assignments. So it has a bunch of, you know, basic but quite effective optimizations that also like apply can be applied at different levels of the pipeline, and that results in generally reasonable code.
Thanks again, Lukasz.
Okay, thank you.